Hello, everyone. I'm a postdoc at ALCF. Yeah, I started working at ALCF about 2 years ago. And in these 2 years, I've been working on this project here that we're calling CFDML. And in one sentence, the summary, the goal is to add data analytics and machine learning for exascale computational fluid dynamics. So this is a little overview. I'll try to introduce the project and what our science goals are, then move on to how exactly we're doing online or in situ machine learning. Then I'll talk a little bit about some performance that we've been able to get recently on Polaris and some that we got on Theta in the past, and then conclusions and some things that we're working on now and will be working on in the future. So introduce a little bit about computational fluid dynamics and turbulence. There's really 4 ways of modeling computations of turbulent flow. On the left here, you have one hand of the extreme, the direct numerical simulation. Here we solve the full unsteady Navier-Stokes equations. There's no modeling of turbulence scales in space and time, and therefore it's the most accurate method, but also the most expensive. In the center, you have the other edge of the spectrum, which is the most common one, RANS, Reynolds average Navier-Stokes. Here we solve for the mean flow directly, and we model all the spatial and temporal turbulence scales. It's the least computationally expensive, but also the least accurate. And then there's sort of a hybrid here. There's 2 hybrids, and they both sort of center around what's called large eddy simulation. Here we solve the unsteady filtered Navier-Stokes equations. And this filtering operation allows us to resolve some of the largest scales of turbulence, both in space and time. And instead, we just need to model the smallest ones, or the so-called subgrid scales. So this is a compromise, both in terms of computational cost and accuracy. And so because of that, this project is focusing on this type of approach. And our goal is to develop what are called closure models for LES using machine learning approaches. And a closure model is really just a model for the unclosed terms, so the basically unknown terms in the governing equations for large eddy simulation. Now, if we were to develop neural net models for these types of terms, these unclosed terms, if we were doing RANs, then this would be relatively straightforward in terms of the workflow, because models are trained on mean flow data. Mean flow data is easily obtained and stored on disk. It doesn't take up a lot of time because you average in time and in space the instantaneous data from your simulations. So offline learning is sufficient and actually preferred in this case. And offline learning really means that we are producing the training data and doing the training separately. But if we are now trying to develop neural net models for LES or some of its variants like well-modeled LES, we really need to train these models on instantaneous flow data. So as our simulations approach or are in petascale or even approach exascale in the future, this means that if we were to save all this instantaneous training data to disk, we would need very large multi-terabyte databases. And so what we are trying to develop is this online or in situ learning framework, which allows us to bypass this problem of saving all these checkpoints and all these solutions to file entirely. And just to be a little bit clearer here, online means that we are producing the training data concurrently with training the model. And an example of a flow that we're trying to target is what you see here, which is a turbulent boundary layer over this bump. And just to give you an idea, this is a petascale type of simulation where one snapshot of training data requires about 400 gigabytes. So you can imagine when you have multiple snapshots on the order of hundreds, this becomes terabytes. But also, we are also planning for this infrastructure really to be beneficial when we go to exascale simulations. But while bumps are insightful, I wanted to share with you what we're really after. And that's really trying to develop closure models. Then we can do these types of simulations that you see here. So these are sort of full turbulence modeling simulations of complex aeronautical and aerospace systems. This is the vertical tail of a commercial aircraft. This is a hybrid RANS and LES simulations. LES would be the region where you see all these turbulence scales. And to add a little bit of complexity, the simulation actually has a synthetic jet. So there's a slit in the surface that's pumping air in and out of the surface. And then this has some beneficial effects For the wing, for the vertical tail, it can produce a bigger side force, but the physics are very complicated. And so the goal would be to train our models on something like this, which is supposed to represent the physics involved, and then apply it to these types of problems. A little bit more on our science goals, where we stand at the moment. As I mentioned, we are using this to train neural net models for unclosed term in the LES equations. So our goal is to be able to predict local and instantaneous subgrid stresses, in particular the subgrid stress tensor, defined here where the tilde is a filtering operator and u is the velocity. Currently, we've been able to demonstrate this, the model that we're working with is predictive on some academic flows, and we're trying to expand it to the flows I've shown in the past two slides. On the right here, you see computed with direct numerical simulation and predicted with LES using this neural net model, the turbulent kinetic energy spectrum decay for this homogeneous isotropic turbulence flow. And just to give you an idea of the savings that we can achieve with large eddy simulation, a large eddy simulation computed on a 32 cube grid, so we're talking about this blue line here on the curve, is about a 500 times reduction in the computational cost relative to the DNS that was used to generate the training data. So there's significant savings with this approach. And that's exactly what we're targeting. Now moving on, how are we doing online machine learning? So we're leveraging a tool that's called SmartSim, and then there's a sort of a sub-tool, part of the same package called SmartRedis, to build our workflows. SmartSim and SmartRedis are open source tools being developed by Hewlett Packard Enterprise, HPE. And I purposely am not going to dive much into the details of SmartSim because there's actually a talk on SmartSim itself. That's part of the Integrating AI and Simulation session that is taking place Thursday from 1 p.m. to 1:30. And here there will be a tutorial, more details on what SmartSim is, and some hands-on exercises specifically for tailored to Polaris on how to deploy some training and inference workflows. So moving on a little bit on how we are doing this particular case, how we're setting it up. Well, we have, first of all, two different types of workflows. They can be combined, but for the purposes of explaining things, let's separate training and inference. In the case of training, we have a CFD solver that is concurrently being launched on a machine such as Polaris, with then a distributed training application. This would be sort of data parallel training, for example. And then also we have a SmartSim database. This is really the power of SmartSim, is to deploy this database in memory. And then we're using SmartRedis clients, also developed by SmartSim, to connect these applications together. For inference, we take away the machine learning component, and instead we do that within the database. So what this means is now we have only two components, and we are only required to send data from the CFD solver to the database itself. We also have two different implementations of this approach. One implementation we call clustered. What this means is that you can see here in this diagram, each component runs on distinct nodes. And so now we have inter-node communication to transfer data from, say, the CFD solver to the database and vice versa. The other approach is co-located. And in this case, basically, this diagram is replicated on each node that we deploy our job over. So now we have CFD solver database and distributed training running on the same node, and we change, and it's no longer communication between nodes, but rather all the communication between the different applications stays within the node. So a little bit more about these two approaches. They're a little bit different, but they perform the same thing, and they have pros and cons for each. So to give you an overview, as I mentioned, the clustered approach, we have a single database, and this database can be sharded or spread across a cluster of nodes. So it doesn't have to be just one node. Each of the components, so this is the database, the CFD solver, which we call PASTA, and the distributed training run on a distinct set of nodes. Some pros of this approach are that all the data is contained within the same database, a single database. And all of this data is visible by all the applications, and specifically all the ranks of all the applications. So it allows us to create the most flexible workflow. This means that we can go much beyond what you saw here in terms of getting creative, and we don't have to have only 3 components, but we can easily attach different components to the database. It's not limited to 2, but we can go up to a large number. Cons, you'll see in a little bit, this approach has reduced data transfer performance, as you might imagine. So it's a little bit less scalable. The co-located implementation, instead, we deploy a distinct database on each node. So as I mentioned earlier, now the 3 components of our workflow, for example, for training, all share resources on each node. So this could be, for example, on Polaris, CPU and GPU resources are shared within the database, the CFD solver, and the training. The biggest pro here is that this is a very efficient way of scaling this workflow, as you'll see in a little bit. The cons are that because we are deploying distinct database, the training data is actually itself distributed across all these different databases. So if we were to access, or if we would want to access from one node, database that is stored, data that is stored in a database on a different node, it's a non-trivial task, but it's possible. This, however, doesn't impact a lot of online and distributed training workflows because the model updates are still done considering all of the data. And you'll see that in a second. Here I wanted to also go a little bit more into the details of how exactly we are doing things. So as I mentioned, Pasta is our flow solver. That's just the name of the code that we're using. And it's mostly Fortran. So this initially also set up a little bit of an obstacle because it wasn't as easy to integrate Python with Fortran. So SmartSim allows us to basically attach to any programming language, as you'll see in the tutorial. So during training, what we do is we first use domain decomposition. So that means that each pasta rank works on a partition of the entire domain. So you see here pasta, and we have, for example, n ranks in this diagram. Now, as Pasta integrates the solution states, we process those solution states also online or in situ. And so we do parallel computations of the model inputs and outputs. And depending on this model, this can require some data analysis that needs to be added to the CFD solver. And then each rank sends the training data to the database with a unique key. And the key has the name basically of the rank that the data came from. So this is how we can distinguish the data within the database. And so in the end, our database will contain basically all of the tensors of training data, all the training data that we decide to send. So this is, for example, number of ranks times number of time steps, distinct tensors of training data. And something to note is that we have the option of sending training data and replacing what is there. So that means that training will be done on one snapshot at a time, or we can add snapshots to the database. So this means that we can train the model on a select number of snapshots from the simulation. And now moving on to what's happening on the other side of the workflow. So here we have a distributed machine learning algorithm, in particular doing, for our case, data parallel training. This, as I mentioned, runs at scale as well, and it runs concurrently with the CFD simulation. This is sort of the key point of online training. And so for each epoch of training, what we're doing is we're choosing a randomly set of tensors that are present in the database. And each machine learning rank will, at the beginning of each epoch, go and retrieve those set of tensors. So in this diagram here, you're seeing, for example, rank 0 is grabbing tensor 0 and 1. And then it's concatenating those and training over those. However, this was just to make the diagram simpler, but the rank number of the tensor and also the time step number are chosen at random. So we're basically shuffling the data before we grab it and train on it. After each rank has grabbed its data from the database, we then perform mini-batch stochastic gradient descent with synchronized optimizer step. And the synchronization part allows us to, as I mentioned, make sure that model updates are done considering all data from all parts of the domain of the simulation. when new data is placed in the database by pasta, the training simply continues with the latest training data. So if it was replaced, we just take the new data. And if we added a new time step, for example, a new snapshot to the database, we just grab it and keep going. So a little bit now about performance. So how does this actually run on Polaris and Theta? So what I wanted to start by showing is some of the overhead of transferring the training data in the case of online inference. I didn't describe exactly how we're doing online inference, but it's fairly similar to training, to this side of training. Effectively, we have pasta and the database, but instead of sending training data, we're now sending inference data and retrieving it back from the database. So what we can do is we can measure the overhead of that data transfer. There's, as I mentioned, two approaches. We have co-located, and that's the blue line. And also we have clustered. And clustered, as I mentioned, we can deploy this database on not just one node, but multiple nodes. So here you'll see that we've deployed it on 1, 4, and 16 database nodes. And what we're seeing on these curves is basically how much time it takes to perform that data transfer as we increase the number of simulation nodes, all the way from 1 to 256, which is about half of the size of Polaris. So first of all, you can see the co-located approach, as I mentioned earlier, is very scalable. The data transfer time is actually almost constant as we increase the number of simulation nodes. This is because we only have data transfers within the node. We're actually not doing node-to-node communication in this case. For the case with the clustered approach, not only is the data transfer more expensive, and again, that makes sense, we're doing node-to-node communication, but we're seeing that as we add number of simulation nodes to the infrastructure, if we don't increase the size of the database, the cost goes up in this sort of linear fashion in this log-log curve. In the case for receiving data, we're seeing that as our database size increases, so from 1 to 16 in this case, the cost of retrieving data becomes almost flat with the number of simulation nodes, but instead on the sending side, which is a little less efficient, we still see that we are increasing with this sort of linear slope. Another thing that we are interested in also, how quickly does the model run? So how quickly are we performing inference? And again, here we're seeing that there is a lower cost of doing inference, so actually evaluating the model with the co-located approach. And this is really because we are limiting the number of inference calls that each database has to handle. In the case of the co-located approach, we basically, the ratio of database CPUs or database resources to simulation resources can stay constant. But in the case of the clustered approach, that's not true. In the interest of time, I'll skip this this is sort of a similar plot for the training approach. And I wanted to finish with this slide, which is basically saying that if we actually then compare the overhead of this communication with how long it takes to perform a time step in our CFD solver, then we really get a measure of this data transfer time overhead relative to the problem we're trying to solve. And we were able to get that down with the co-located approach to below 1% of a solver time step, which for our purposes meant that we are doing inference very efficiently. And actually, we were able to beat the initial Fortran implementation in the CFD code, which was doing inference, basically writing the weights and biases of the model to file, uploading them, and then just using a Fortran subroutine to do inference. So that was a good success for us. So to conclude here, we basically developed a software infrastructure that allows us to combine computational fluid dynamics with online machine learning at scale. We can do both online training and inference of neural net models efficiently. And also, our co-located implementation shows effectively a constant data transfer cost with increasing scale, which means that the cost of or scalability of this infrastructure really depends on the application itself. So in this case, the CFD solver and the data parallel training, for example. And then, as I mentioned, we're currently using this infrastructure to develop turbulence closure models for large eddy simulation, but we have ongoing future work that is expanding that to tackle more problems, more CFD solver. And we're also incorporating with a GPU-enabled version of our CFD solver so that we can really make use of the GPUs on Polaris and future systems like Aurora. So that I wanted to see if there's any questions, and apologize, I went over a little bit.
Can you hear me? I have a question.
Yes, sure.
I mean, very interesting work in press. So what's the advantage of using traditional Smith-Skransky subgrid model compared to what you try to do use machine learning to do that? Mm-hmm. I'm very interested in this, why you not using Smith-Skransky or the typical LES subgrid model, because you are trying to closure, right? Mm-hmm. So what's the advantage? I'm trying to understand what you try to do that.
That's a great question. Yes, let me know. Let me see if I have something in the backup slides. I didn't include it in this presentation. So okay. what the PIs of the project that I'm working for have able to show in the past, and that's sort of the groundwork of this work, is they were able to show that this neural net model that was trained from homogeneous isotropic turbulence was giving better accuracy than Smith-Skransky. And not just on homogeneous isotropic turbulence, but also they looked at other sort of free shear flows. They looked at a Taylor-Green vortex too, for example. And in that case, it was much less dissipative in the transition part of sort of the initiation of turbulence. And so was just effectively giving better predictions than Smith-Skransky. And we also know that Smith-Skransky suffers as we go to wall-bounded flows. And so that's where we think we can really go ahead of that traditional type of model when we start training and apply this to wall-bounded flows.
Yeah, does this work you guys did is open source or just in-house?
There's some papers about this, and I can share those in the Slack later if you would like.
Okay, appreciate it. Thank you.
Yeah, of course. Thanks.
Hi. Do you plan to use GPUs for the front-end part of the code or just for the Python learning part?
We are planning to use GPUs for both. What we are working on right now is incorporating our current workflow, which has a CPU-only version of the CFD solver pasta with the GPU version of it. And so the goal there will be to use GPUs mostly for the CFD solver, because for some of the models we're looking at, that is actually the most expensive part, is actually integrating the simulation. But the goal is to, in general, use GPUs for both simulation and machine learning.
Okay, thanks, Riccardo.
No problem. Thank you.
If there are no more questions, I propose we move on to our next talk, just from Steve Rangel, also talking about an application use case. Steve, are you ready to go?
Yeah, let me share my screen. Okay, so can you see my screen and hear me fine?
I see your screen and can hear you just fine. Take it away.
Okay, great. Yeah, so my name is Steve Rangel. I'm a computer scientist in CPS division, one of the core HACC developers. So I'll be giving this application case study of HACC running on Polaris. And a lot of these sites are in conjunction with Adrian Pope and Nick Frontieri, also two of our HACC developers. So just a quick overview about HACC, some of the background, gravity only and hydrodynamics, some of the data products and analysis that come out of HACC. And then I'll talk a little bit about the work that we did on Polaris, and this is with respect to subgrid model parameters and tuning them to give good results for simulations. So I guess a good question is, why do we run HACC? So HACC is an embodied simulation code for cosmology. It's very important for theoretical research. So it's understanding large-scale structure formation, looking for signatures of new physics, comparing with observations. There's only one observed universe, so a lot of forward modeling is very important. So comparing with results from LSST, it's also very useful for creating mock universes, so mock catalogs from which survey designs sort of can influence survey design. So future surveys and their parameters can benefit greatly from having some of these mock catalogs that simulations can provide. Just understanding theoretical models, summary statistics are very important. So simulations play an important role. So about HACC, so the HACC is an embodied solver. It solves gravity. Gravity is infinite in extent. It's unshielded. It dominates at the very largest scales. So computationally, it's a challenging problem to solve. So as the universe expands, structures condense from the very smooth initial conditions. So I see this upper left box as a visualization, the positions of particles very early on in the simulation. And as the simulation evolves, then you start to see a lot of clumping together of the matter. The visualization you're seeing here is a visualization of the dark matter. So dark matter is a dominant form of matter. It's something like 5 or 6 to 1 with the ratio to the baryons. But baryons are very important. So hydrodynamic solvers are what we use to solve the physics for baryons. It's subdominant as far as the matter component. And the physics is adiabatic, gas, temperature, pressure shocks. And if we want to understand sort of what's happening at a smaller scale, star formation, feedback, those are going to be modeled using subgrid models. So I like to show this slide just as a kind of a behind the scenes or under the hood sort of how HACC works. And this is a sort of a perspective from the time integrator. So at the very long range, force of gravity is calculated using a spectral method. So it's the Poisson solver. This is a distributed FFT, and all of this is written in C and C++ and MPI. A lot of this right now, at least currently, runs on the CPU. The more computationally intensive part of HACC are the short range solvers. So this also includes the hydrodynamic solvers. And this is done using a leapfrog method. So this kind of time integrator is the leapfrog integrator. And this is also hierarchically carried out. So the gravity short range is solved, and then sort of nested within that is the hydrodynamic solvers that run. These also have some effect on the time integrator. I won't spend a lot of time on this. So part of the analysis, so what are sort of the data products that HACC produces? Well, dark matter halos, or dark matter collects into these overdensity formations called halos. They're very deep gravitational wells where baryonic matter collects, eventually cools, condenses, forms stars and galaxies. Roughly half the mass in the universe ends up in these halos by this current epoch that we are in. And halos are identified by looking for these overdense structures. And these are using sort of density-based clustering algorithms. Halos also sort of form in this kind of hierarchical way. So they interact with each other by colliding and merging, and depicted in this image here, sort of the centers of these smaller halos, and as they merge with larger halos, those centers also remain as overdensities in this larger structure. So this interaction history is very important because interactions between galaxies can trigger epochs of star formation. So it's very important to sort of keep track of this merging history. Part of the analysis is determining this history, and this is sort of more formally known as a merger tree. So this data product is sort of important to study, especially when creating like these mock catalogs that I was describing that are very useful for surveys. From that cartoon picture, this is more of a realistic image actually taken from simulations. This is sort of those trajectories of cores from a very large halo. And you can see that these tightly bound cores of tightly bound groups of particles, they're cores from these dark matter halos, are not very easily disrupted. So they remain sort of very tightly bound. And they're good positions for galaxy proxies. So like I just mentioned, sort of understanding this formation history is very important, particularly when creating these like galaxy catalogs. And one reason is because these cores are actually very good proxies for galaxy locations. Another data product that comes out of the simulation are these halo light cones or light cones. This is a particle light cone. So we can sort of simulate what an observer inside the simulation would see. So because the speed of light is finite, as we look at objects that are farther away, they appear as they did further back in time. So because HACC runs this fixed size box with periodic boundary conditions, if we want to generate something like a light cone, this is an additional piece of analysis that needs to be carried out. But like I mentioned, sort of the objects that we're interested in are these dark matter halos and these overdensities. So another sort of data product of interest is a halo light cone. So halo light cones are sort of a little more complicated than just regular light cones with particles. The way we do it is we take into account the formation history of the dark matter halo and look at where it actually crosses the light cone. And then using that information, we can sort of output the more appropriate object. So in this case, two smaller halos were merging. The more dominant halo, the larger mass one, is the one that we use when crossing the light cone. It's sort of a more sensible approach. So I was talking mostly about gravity-only simulations. So what are some of the limitations of HACC? Well, it doesn't produce galaxies directly. The position, shape, luminosity, all of these things are not directly output by the simulation, or it doesn't directly get simulated. It's a very large dynamic range, so you need very, very large volume simulations to get realistic structure formation information out of there. The computational intensity increases dramatically as the resolution of the simulation increases. And self-consistent creation of realistic galaxies within a cosmological volume and body simulation is beyond an exascale problem. So like I was mentioning, some of the physics that drives like star formation is obtained from modeling. So so sort of what then so what's next, I guess, or what's sort of the current state of what we're doing. So sub-resolution modeling for modern cosmological survey predictions is sort of was the goal of a lot of the recent work. So we're developing calibrated models that emulate these astrophysical processes at scale smaller than those resolved by simulations. And we're trying to utilize results from high-resolution galaxy formation simulations. So simulations that actually very carefully model galaxy formation and that are performed at a much higher resolution. And because they're such at a much higher resolution, they're much smaller in volume. So we're talking about simulations that are just simulating the formation of one galaxy. So that makes actually the problem much more tractable. And we're doing a lot of this in collaboration with the group at Northwestern that runs it's a code called FIRE. And we're implementing new models within this CRK HACC framework. So this is basically the hydrodynamic version of HACC. And the goal is to fully calibrate and validate the implemented models to the relevant science targets. So the scope of this work is developing these subgrid models for galaxy formation, doing sensitivity analysis on the parameters. Like I said, these are models, they're not directly simulated. Calibration and verification or validation of the observables, making sure they're performant on accelerated hardware, and developing new integration techniques that are scalable for the cosmological volume, cosmological size simulations. So the suite of subgrid models so far that are implemented are UV backgrounds, metal line cooling, chemical enrichment, AGN kinetic and momentum feedbacks, and supernova with galactic winds. And a lot of these, some of these parameters are sort of influenced by the FIRE simulations. The image here sort of depicts sort of what some of these feedback models can do. So this is a density plot. And you could see, when some of these feedback models are enabled, you have a lot of the densities that are much more sort of blown out in regions where you saw much tighter concentrations without them being enabled. One other thing that we've done sort of very carefully, over the course of the past couple of years, is comparing HACC with another code, NICS. So NICS is a grid-based code. So HACC is a particle-based code. NICS is a grid-based code. So it's the Lagrangian or Eulerian views of simulations. And we've done a lot of validation without tuning a lot of other simulation parameters to see how well of an agreement the two codes can be. So we're looking at temperature plots that are function of density or background density ratios. And you see HACC and NICS have quite strong agreement. The Lyman alpha in this upper right corner, Lyman alpha flux, I think this is actually the first time that a Lagrangian or Eulerian code have agreed to the 1% level. So this was also quite a successful result. And the star formation convergence. So compared to another simulation code, Arepo, similar size volumes with particle densities are yielding very similar results with star formation rates. So this is some of the checks that were also very important and look very well. So some of the work that we're trying to do is calibrate simulation. So we're trying to improve subgrid models, making sure they're performant on the exascale hardware. Subgrid models sort of affect that whole computational workflow. And first results from this analysis pipeline, so we're measuring things like the global galaxy stellar mass function, the stellar halo relation, and star formation rates. And then the next thing that needed to be done was to complete a suite of simulations and then calibrate these models to observations and measure some things like outflow rates, for example. So this graph on the right is depicting the star formation rate One thing you can notice here is so universe machine. So UM is a modeling technique software that's called universe machine. It's just closest thing, I guess, to what we would expect as a desired result. And you can see with this red line with star formation only, we're quite off. And then as we start to add like feedback models, we start getting actually closer to what we think the correct answers should be. Similarly, if we're looking at something like the galaxy stellar mass function. So this galaxy solar mass function is basically sort of a binned histogram of the stellar mass in bins. So this on the horizontal axis, we're looking at a log scale stellar mass bins. So this, so for galaxies that fall within this stellar mass bin, we're trying to basically keep a count, right? So this is the initial results are not that great. So some tuning needs to occur. So finally, sort of what we're trying to exactly what the science was done on Polaris. So we ran a whole series of these smaller 32 megaparsec simulations. These are basically run on 2 node jobs of Polaris. Each one is with 3 or 4 hours of wall time. And the idea, and I'm showing one here, but this is a result of a whole series of simulations that were run. I don't know the exact number. It's somewhere in the neighborhood of about 80, I think. And from these simulations, we've been able to tune all of these subgrid parameters. So what you see here, the blue and like light orange color is two different ways that we can measure the stellar mass for galaxies. And we can see they're actually in quite good agreement with a number of different predictions using universe machine and Trinity, TNG, and Illustrious are other cosmological simulations. So this is great. So then the idea was, but as you could see, sort of on this sort of tail end here, close near this 10 to the 12 mass, we don't have very many objects, and that's because these cosmological volumes are just too small. 32 megaparsecs, just too small for there to be large enough halos and large enough galaxies that would actually have objects that are representative in this area, in these large mass bins. So to do that, we need to run larger scale simulations. So this is actually a 256 megaparsec simulation that was run on Polaris. So now using those same parameters found from those large number of small runs, and you can see now we do have sort of tighter error bounds and enough objects to be able to confirm that in this larger regime, larger mass regime, we actually get very good agreement too with the simulations and universe machine predictions. So this is actually very good. This simulation is this 256 megaparsec simulation actually runs on between 128 and 256 nodes of Polaris. That reason is the size of the volume increases cubically. So 256 megaparsec simulation is 500 times bigger than a 32 megaparsec simulation. So the number of nodes is sort of as expected. It's what you would need to carry out this larger volume. And I think this is the last slide I have. Thank you for listening.